Okay, those of you who are in A push, we're going to do a lesson on parametric equations. And when I was trying to decide how to introduce this lesson, I decided to let Khan Academy do it. So this is just a short video to get you an idea of what a parametric equation is used for, and then we'll dig into actually the technical part of what they look like on the calculator and how cool they can be. So I hope you understand some stuff that Khan does here. Hang on, let me see if I can get him back to 0. All right. Oh, I bet they can't hear this.
On this cliff, I have a car. This car is not sitting on the cliff,
I've
it's
got
driving off the cliff. Driving off this cliff at 5 meters per second. 5 meters per second. And I want to know what is the path of this car as it falls off the cliff. So let's set up a little coordinate axis here. Let's say that get my y-axis. This is the y-axis right there. This will be my x-axis. X-axis. This is y. This is x. Let's say that this is the point. Well, we know this is a 50-meter high cliff. Maybe y equals 0 is sea level. This is 50 right here. And let's say that this point right here on the cliff, that's at x is equal to x is equal to 10. So this point right here is 10 times complicated. Let's say the car is right at this point, right about to drive off the cliff. Time is equal to 0. Time is equal to 0. For time is equal to 0. So my question is, what happens if the car drives off the cliff? This is a bit of a physics problem, but I won't go deep into the physics, and I won't prove some of the equations. I encourage you to watch the kinematics videos and the projectile motion videos if you want to know where the equations come from. But the point here is just to get the equations and see what the graph looks like. So if I want to know x as a function of time, x is a function of time. This is a really vibrant color. X as a function of time is really important. Well, we're going to assume that we're on a planet that has no air. We're in a vacuum. So if we start off at the x direction at 5 meters per second to the right, we won't be decelerated by air or friction or anything else. Newton's laws of motion, an object in motion stays in motion unless it's affected by a net force. There won't be any net force in the x direction. It's just going to keep moving to the right at 5 meters per second. And position or distance is just equal to velocity times time. Velocity is y times time. And of course, it didn't start at time at x is equal to 0, right? This is at time equals 0. So it started at x is equal to 10. So if you want to know this kind of x of 0, where it started off, so plus 10. And this should be a little intuitive for you, right? If time is equal to 0, this term cancels out, where x is equal to 10. That makes sense. If time is equal to 1, you should know that it will be 5 meters further out, so on. Fair enough. That's x as a function of the parameter time. As you probably realize that this is a video on parametric equations, not physics, so it's nice to early on say the word parameter.
parameter. That's he. Sometimes he makes me laugh.
Hence, the parameter. People talk about parametric equations. Well, it could be anything. It could be radius or angle or who knows what else. So let's figure out what y is as a function of time. So y as a function of time is going to be equal to the initial y position, or y of 0, which is 50 meters up in the air, 50 meters up in the air, plus our initial velocity in the y direction. And we don't actually have any initial velocity in the y direction. The car isn't jumping or isn't diving. It's just moving horizontally to the right, and the cliff is supporting it. So it's not, it has no y velocity, which we're curious if the y velocity times time. Since there's no y velocity times time, at least initially, I'll put nothing there. Plus the acceleration of gravity times. So initial position, we had no velocity times time, so we'll do that. Minus 10 meters per second squared times 10 to the power 2. And you can watch the projectile motion videos to figure out how I got these formulas right there, but that's not the point. The point of this is to graph what happens to the car as it approaches the parametric. So what is the path of this car as it falls off the cliff? Let's make a table here. Let's make a table. X and y are a function of this third parameter, t. So we're going to set t as different values, and we're going to figure out what x and y are equal to. I'm just going to arbitrarily think of t is equal to 0, t is equal to 1, 2, and 3. If time is equal to 0, what is x? X of 0, this is 0, x is equal to 10 meters. And time is equal to 1, what is x? So this is x of 1, right? If I wanted to write that notation. So 5 times 1 is 5 plus 10 is 15. X of 2, 5 times 2 plus 10 is 20. And it makes sense. Every second we're getting 5 meters more to the right, or x is increasing by 5 meters. So t is equal to 3. 15 plus 10 is 25. Easy enough. The y is a little bit more complicated. Just to simplify this, let's say t is 5, right? 10 divided by 2. So 15 minus 5 t squared. So time is equal to 0. This term cancels out. We just have 50 meters up in the air. Time is equal to 1. 1 squared is 1 times 5 is 5. 50 minus 5 is 40, 45 meters in the air. Is that right? Time 1, 50, right? And then time is equal to 2. 2 squared is 4. 4 times 5 is 20. 50 minus 20 is 30. And then finally, at time is equal to 3, and I just say finally because that's the last number we picked. Time is equal to 3. 3 squared is 9. 9 times 5 is 45. 50 minus 45 is 5. So let's plot these points. So time is equal to 0. That's what we got right there. And time is equal to 1, where x is equal to 15. Let's put this is 5, 10, 15, 12, 15, 20, 25. And then the y-axis, now while we're at it, so this is roughly 10, 20, 30, 40, 50. So time is equal to 0, we're at 10:50. That's that point right there. And time is equal to 1, we're at 15:45. So x is 15, y is 45. Let's just write it up there. So this is t is equal to 1. And time is equal to 2 right away. Is that before 20, 30? So 20. So this is time is equal to 2. And then at time is equal to 3, we're at 25, 5. So we're right there. 25, 5. Time is equal to 3. And if we kept going on, at some point we're going to hit the ground, and you can figure out, actually, set this equal to 0, and you figure out the exact time. It actually doesn't matter. If this is equal to 0, if we take t is equal to this, we're just a little over 3 seconds, which makes sense, right? A little over 3 seconds, we're going to be hitting the ground. But anyway, what's the path of this car? Does it look something like this? It's going to look like this. Ooh, it starts getting accelerated downwards, and then plunk, it hits the ground at 30 point something seconds. Now, what was interesting here is that by setting the parameter, not only did we get the curve, right? We got this curve, which is kind of half of a parabola, half of a downward tipping parabola. And we can actually eliminate the t and just get the equation for that. We'll do that in future videos. But what was
I'll teach you how to
interesting
do
is
that
we know
today.
the parametric equation. We know the direction of the car. We just know it's a graph, not a car and everything else. We don't know which way the car is falling. But now we know that as t is increasing, we're going in that direction. So we can draw some arrows here. So because it's a parametric equation, we can draw some arrows. And then the most important thing is we know exactly where the car is at any time t. You can substitute t is equal to 1.25 seconds. You know exactly where the car is. So you can plot these points, and you can kind of get a sense that as time goes on, we're getting accelerated downwards. And that's why for every second further, especially the y distance gets further and further apart. Anyway, I just wanted to give you this example. All of this is easy to follow. The intention is to give you the notation behind
Okay. Stop this first. Okay, so let's go back. Now, we're going to get in the textbook. And I'm told that most of you don't have your textbooks, so that's okay. We can function. Um, what I want us to do is get your calculator, which you have, and let's follow through your notes, okay? Now, what we're going to do first is we're going to graph x equal t, y equal 3t minus 2. And we're just going to graph this to just play with it a little bit. Now, you have to be in parametric mode. Oops. Now, the only time radian or degree will matter is if we have a trig function in one of our equations. Otherwise, it doesn't matter. Now, you'll notice I hope after you watch that video that it makes sense why these are in pairs. You have to do an x and a y to get a picture. I don't want that, though. Let me fix that. I just want the old, I just want a line. I just want a line. Is that, that may be up. There we go. That's all I want. Okay. All right. So let's graph that. Let's put in x equal t. X. Come on, Stennett. Dadgummit. What's the matter with you? There we go. And 3t, what did I say? 3t minus 2. Now you're going to need to look at your window. Now this window, I don't know how yours is set up, but this window is still set up 0 to 2 pi. Well, we don't need that because we're not dealing with trig functions. But if we think about time, I'm going to let my time start at 0, and maybe I want my time to go to 10 seconds. And I'm going to count by 1 second. Now let's leave your x min, x max, y min, y max just like this, because I think that'll kind of make a square window. Now let's graph it. Now you'll notice, you're like, hey, that's a line, but it's not the whole thing. And you think, well, why not? I want you to hit the trace key, and trace is not something I use very often. But do you notice it gives you all three variables down here? T is your parameter, and it tells you when t is 0, it tells you this is what x is and this is what y is. Do you notice that it graphed the line 3x minus 2, y equals 3x minus 2? That's what you see there. You just don't see it all. Now, if you just start hitting your right arrow key, notice that what it does, we said t step was 1, so that thing's going to count off your t in increments of 1, and it's going to tell you when t is 1, x is 1, and y is 1. When t is 2, x is 2, and y is 4. Now, if you'll notice, I went all the way to t equal 10, and notice it won't go past it because I set t from 0 to 10. Okay? Are you all right? If I had done this, see, it would have graphed more of the line. Okay. Now, let's go back. Let's talk about number 2 in your notes. A rock is dropped from a 420-foot tower. Write an equation for the rock's height above the ground. Now, this is where Kahn was getting into the physics problem. If you are in feet, in standard American units, have you ever seen that equation? You probably saw it in Algebra 2. This number right here is acceleration due to gravity. This is your initial velocity. And this is the initial height above the ground. That's what the sub-zeros mean, the subscripts of 0. And remember, Con was talking about the car going off the cliff? There was no initial velocity in the y direction. It wasn't being pulled down or up. That's why there was no vertical velocity. But now, we are in just standard old mode here. So let's look. Imagine that a rock is dropped from a 420-foot tower. Where does the 420 go? Yeah, 420 is going to go right here because that's the height from which the rock was dropped. Now, the initial velocity, if you just drop something, you have no velocity behind it. If you throw it, there's initial velocity, okay? I was watching the Razorbacks play baseball last night. Wasn't it? Man, I heard at one point, one of the guys, and it may have been the announcers talking about a different game, I can't remember, but home run, and there are actually trackers that will measure the velocity of the ball coming off the bat. There are, if you go to like a Razorback game, it'll clock the speed of the pitch, so the velocity. When one of these guys hit a home run, the ball came off the bat at a speed of 117 miles an hour. Yeah, that's why you want to be a pitcher and get hit in the head with one of those, with a like that, 117 miles an hour, hit you square in the forehead. Not a good thing. You wouldn't be a pitcher anymore, yeah. So the equation for this one is going to be negative 16t squared. The ball was dropped, so there's no initial velocity, plus 420. Does that make sense? Now, I want you to look at number 2a. It says to graph this in function mode. So let's go to your calculator. And we're going to go back to function mode. Negative 16t squared. Now, why is it going to give us an x instead of a t? Because we're in function mode, right? Now go to your window, and I want you to set your window like this. I was playing with this last night, and I'm going to admit to you, when I was working on this last night, it was like near the end of the ball game. And I didn't even see the end of the ball game because I fell asleep. So I had this in my lap, and I fell asleep. So, oh. Do you notice when you draw a function in function mode, it graphs left to right, period. That's what it does. Now you know that some of this doesn't make any sense for this problem. What doesn't make any sense for this problem? Negative what? Negative height doesn't make any sense. And why does negative x not make any sense? Because it's negative time. So only a piece of this actually makes sense, and that's the part in quadrant 1, correct? As well as the point right here and the point right here. Now, so let's talk about how to do this in parametric mode, and let's see how much more information you can glean from doing it in parametric mode. Now, let's look at your B. Look at number 2B. Let's go back to parametric mode. Now you're going to type in x is 2.5 and y is negative 16t squared plus 420. Now, before you graph, I want you to, I want to explain to you what this 2.5 is. The 2.5, if a rock is being dropped, just dropped, it's not moving this way, is it? Okay, so what we're going to do is we're going to model the drop of this rock on the vertical line x equal 2.5. Now let's go back to window. Since we know we're dealing with time, we're just going to we're going to start with t equals 0. We're going to leave that and we're going to play with it. And we're just going to see what happens. So go ahead and graph. And you're like, where is it? Really? Trace. Now I want you to take a look. At time 0, that rock is 420 feet above the ground. Does that make sense? Sure does. Now, hit your right arrow key one time. At time 1, that rock is 404 feet above the ground. At time 2, it's 356 feet above the ground. And you can just keep going, and you can see how much more, as t gets bigger, how much more the rock falls. And that's because of that acceleration due to gravity. The gravity's pulling it toward the ground, and so that acceleration, it's getting faster, so the rock is dropping faster. Now, it's not going to make any sense past here, is it? This x equal 2.5 was just giving the rock a place to demonstrate its drop. I could have put that at 3 or 4. It wouldn't have mattered. But what's nice about this is you know immediately at any given time where that rock is. Do you remember when you were learning stuff like this at the beginning? And I don't mean beginning of this class, I mean like Algebra 2, maybe Algebra 1. And you'd get a graph like this, and your teacher would say, now that's not the path that the rock follows. Do you remember that? If this is x and this is y, the x stood for time, and the y stood for height. And all this did was it said at time 1, the height was this, and at time 2, the height was this, and at time 3, the height was this, and at time 4, the height was this. All that modeled was the height with respect to time. But so many people, you want to think, oh, then that means the rock is taking this path. The rock is going this way. And that's what parametrics will do for you. It will help you to see the actual path because you've got that third parameter. Let's go to C. Go back to your calculator, and it says change the x equation just to t. Now it looks like the function one, doesn't it? Now let's trace and see what we get. Wait a minute. Am I in function mode? Yeah. There we go. Now just trace, look at the numbers, just see what happens. Which way, letting x equal 2.5 or letting x equal t, is a better model for what this rock actually does? Because the rock is dropped, so it's just vertical motion. But do you understand when we make it this way, it's still telling you at this particular time, the rock is going to be 20 feet above the ground, or meters in this case, I think, by whatever feet. All right. Look at number 3, and I'm trying to remember why I put so much space down below that, because I can't remember. So we're not going to worry about it. Look at number 3. These equations with t are examples of parametric equations, and the parameter is t. As is often the case, t represents time. Now let's look at that number 4. This is just a little bit of reading. When we give parametric equations and a parameter interval for a curve, the parameter interval is the t-min and t-max and t-step. We have parameterized the curve. A parameterization, say that 3 times fast. Consists of the parametric equations and the interval of t-values. So your t-min, t-max, t-step. Sometimes parametric equations are used by companies in their design plans. It's then easier for the company to make larger and smaller objects efficiently by just changing the parameter t. Now, so we're going to take a look through some problems in your book. Now, since there's only one book plus mine, we'll function with it. It'll be all right. It'll be all right. Yeah, there you go. All right. So what we're going to graph, we're going to go to your calculator and we're going to graph t squared minus 2 and 3t. Okay? And what we're going to do, we're just going to look at them on some different t intervals. So go to your calculator and put those two equations in x1 and y1. So what did I say? T squared minus 2. Well, no, that's not where I want it. T squared minus 2 and 3t. Now let's go to your window. Let me see how I want. Okay. Let's make your window, we'll talk about t in a minute. Let's make your window x min and x max go negative 10 to 10, and make your y min and y max go negative 10 to 10 as well. And make your x scales and y scales by 1. Now let's go back up to the t min and t max. Let's graph it from negative 3 to 1. We're going to graph this on 3 different t intervals and just see what happens, okay? Now let's graph. That's kind of odd. Now, I'm going to go back. Let's change your t-step. Let's change your t-step to 0.1. Why is that more of a smooth curve as opposed to the other one that looked more segmented? Because you're plotting more points, that's right. In this case, you're going from negative 3 to 1 by 0.1. So negative 3, negative 2.9, negative 2.8. You're plotting a point at each of those t values, okay? Now, did you notice how, where did the graph start? Where? Started here? Is that where it started? Because to be honest with you, I didn't pay attention. If you do trace, that tells you exactly where it started. When t was negative 3, your x value is 7, your y value is negative 9. And then if you trace, you can actually watch the path. Go back to your window, and I want you to do the same thing, but do it on the t interval negative 2 to 3. Well, let's just take a look then. Okay, we are looking at number 7 in your notes. Yes, we skipped number 6. I'll come back to it. But what I'm trying to do is eliminate the parameter. So I'm trying to get rid of the t's and write this as one equation with just x's and y's, no t's. So what we did is we started right here. I rewrote that as t equals, so I divided both sides by 3. Then I substituted that into t in the other equation. So it'll be y over 3 squared minus 2. So now what I'm trying to do is make this equation now say y equals. How am I going to make that say y equals? Add 2. Multiply by what? Yep. So I'll have 9x plus 18 equals y squared. Square root, so I'll have y equals plus or minus the square root of 9x plus 18. That, oops, that equation right there in function mode is the same as this equation in parametric mode. Now, why the plus or minus? Go to your calculator, put it back in function mode. Can't do plus or minus. So what you're going to have to do is do this. You can look right down here and see the history of the buttons I pushed. But long story short is, here's what I did. I took the negative, and then I did alpha trace. Now, let's do a zoom 6. It's the same picture. But do you notice on mine, it's nice with the color. You cannot graph. The blue one is a function and the red one is a function, but together they're not. So you have to do this one in 2 parts when you do it in function mode. Also, did you notice that this thing graphed from left to right? It started here, went this way, then started here, went this way, okay? Left to right. Now let's go back to number 6 in your notes. Number 6. And it says example 2 on page 476, which if you don't have a book, you don't know. X equals 1 minus 2t, y equals 2 minus t. That's the parametric equation for something. We don't know what it looks like. Let's graph it and see what it looks like. Go back to parametric mode. Ah, come on, Stennett. And it was 1 minus 2t. And 2 minus t. Trace. Notice where it starts. Now, if I decide to make the t bigger, what if I went negative 10 to 10? What do you think would happen to the graph? There's more of it. If I trace, now let's see, I don't know where's my cursor? My cursor's way off the screen. Looking at the x and y values, I can tell my cursor's way off the screen. Doesn't come on for quite a while. Okay. Long story short is this is some kind of line. So let's go back here and let's see if we can figure out what kind of line it is in function mode. Let's take either one of those equations and solve them for t. Which one? Okay, let's take this one and solve it for t. That's going to be t equals 2 minus y. If I substitute that in here for t, what am I hearing? So I get x equals 1 minus 2 times 2 minus y. So x equals 1 minus 4 plus 2y. X equals 2y minus 3. But that doesn't help me. I need to get this in some different form to make so I can know what it looks like. What do I want it to say? Yeah, let's make this thing say y equals. Yeah. We did number 7. Number 8 says, look at example 4 on page 477. I'll tell you what we're going to do. Since like half the class isn't here, all right, number 8. Number 8 says, look at example 4 on page 477. Your mode is going to be an issue on this one because it's got trig functions in it. You got x equal 2 cosine t. Write these down under your number, what did I say, number 9? Number 8. Number 8. And 2 sine t. And we're only going from 0 to 2 pi. So let's graph it. Polar mode. Have you got this down? Why did I say polar mode? Parametric mode. I'm dumb. Yeah, well, sometimes I... Thanks, Taylor. I love you too, sweetheart. It's all right. We're good. What did it say to do on your window? Yep. Let's go in increments of pi over 24. I know I'm going to want to change this. Let's go, I think, I never can remember if I want to go -6 to 6 on the x's or -6 to 6 on the y's. Is this the way I want to do it? Yeah. Holy smoke. Look at that. That's a circle. That's a circle. What's the radius of that circle? I know the bells are not ringing. What's the radius of that circle? 2. So what this ought to be giving us, that ought to be giving us x squared plus y squared equals r squared, right? So because the center's at the origin, make a note. We need to back up and finish right here, okay? No homework. Enjoy your weekend.